this is work that's been going on for a while with my former student, Mingyu Kang, who is now left and he's at Google. So my talk is going to visit many different things. It's a journey through multiple concepts, and it's a 45-minute talk, so it's going to be quite intense. So I'm hoping to make it palatable with a lot of pictures. So stop me at any time if something is not quite clear. So the problem that we're trying to solve is given a graph, and the polynomial system that we're going to think about. There are other ways of thinking about the polynomial system, but this is what we're going to do. You're given a graph with distances on the edges, and you want to find if there exists a realization. In other words, coordinates for the points. And in this case, we're looking at realizations on the plane. In addition, we're going to be looking at planar graphs, which are topologically planar graphs, but we'll come to that later. So we want to find the coordinates of these points in such a way that the given distances are met. So the polynomial system that we'll be concerned with looks like this. I just wanted to say that, you could be looking at a different polynomial system. So you could use, for example, the fact that distances, Euclidean distances, must satisfy the Cayley-Menger equalities and inequalities, which essentially look at a certain matrix and assert that the principal minors, which corresponds to volumes of simplices of that should vanish in a certain dimension, do vanish. And then in addition, they have inequalities that say that the distances essentially come from real realizations. But in this case, you would be solving polynomials whose variables are the distances. So one possible way to try to do this, to think of the realization problem, is that you're given a partial distance matrix and you're trying to fill the remaining distances using these Cayley-Menger determinantal polynomial, setting them to 0. So in other words, finding a point on the determinantal variety. So one way to do this is to find a good set of distances that have not been given. And then after that, sort of have a mixed approach where you use those distances. If they're good, we'll talk about what good set of distances would be. In other words, a particular graph. You fill those distances, and then you find the point coordinates, perhaps using the approach that I'm going to talk about. So in other words, you could potentially combine the two approaches. More on this a little bit later. This is a busy slide, but just wanted to mention it for completeness. So 2D realizations of linkages, by linkage in this talk, I mean a graph with specified lengths on the edges. So already the existence of a realization is NP complete. I'm putting this R here, which is a little bit of a technicality in many people's worlds. In other people's worlds, it's a major difference. Is whether or not you're able to represent a real number in a computer. So the assumption that if you actually can work with real numbers and just think about the algebraic complexity, that set of complexity classes usually have the superscript R in them, as opposed to if you are using our usual computers with bits and finite precision, then they don't have that R in them. But in any case, the existence of a realization is NPR complete. It's in NP because the solution itself, which is a real number, would be the certificate that you can verify using computations on real numbers. And it's NPR hard. And there's proof that basically shows reduction from Kempis universality theorem. The hardness proof, of course, depends on the solutions being of varying dimension. What we are going to be using is isostatic linkages, which means generically they have all 0-dimensional solution set. So this hardness proof doesn't necessarily work. But there's I wanted to go over this, that the different problems that are related to realizability that relate to rigidity and infinitesimal rigidity and so forth. In our case, we just care about d equals 2. You can ignore the stuff below this. Just there for completeness, you can see that the relationship between the complexity of these various different problems, if you're just for a given graph, if you wanted to check, given framework, you wanted to check infinitesimal rigidity, you would just have to check the rank of a matrix, and so that can be done in polynomial time, a given matrix. And these are the general complexity, just to give a calibration of what complexity different problems have. Okay, so if you so for Henneberg 1 graphs, just the question of the existence of realization, Henneberg 1, they're also called zero extension graphs. What you have, we'll talk about this idea of a recursive decomposition of the graph into subgraphs that are also rigid, the original graph may or may not be, but rigid subgraphs, maximal rigid subgraphs. You can do this by each time adding 1 degree at one vertex at a time. That's what the definition of Henneberg is. So you're solving this polynomial system in this way. So you basically have the certificate, a combinatorial certificate that essentially simply tells you, as you solve the graph, as you put 1 vertex at a time, which side of what the orientation of that vertex is, in particular, the orientation of the triangle, clockwise orientation of the triangle, whether you put this vertex here, for example, or on the other side. It tells you that's a 1-bit piece of information. So if somebody just tells you a whole list of bits that says, you put it on this side, you put it on the other side, and so on and so forth, you have a certificate, which is an integer certificate. So in that case, you don't even have to have a real number here. You just have an integer certificate, and once somebody gives the certificate, you simply solve some quadratics, one quadratic system for each point, and basically assuming that you believe that the quadratic solving doesn't require real number storage, then you actually have a NP membership for such graphs. Okay, so the key thing here is that this the way in which we did this is we have a way of decomposing the original graph into a whole sequence of smaller graphs, starting from just at an edge, and then one triangle, another triangle, and so forth, 1 vertex at a time. It's a recursive decomposition of this large graph into successively smaller graphs. You could think of it that way, or building it up from the bottom. And you can do that in a purely using just the graph, and that plan, that combinatorial plan that you get, then allows you to do the algebraic work of actually solving the system. So it's also in NP for a slightly larger class of graphs, which are called tree-decomposable graphs, which where you put graphs together, 3 graphs together, three tree-decomposable graphs together, such that pairwise they share a single vertex. The whole decomposition proceeds almost exactly like the Henneberg one that we just saw, and there's a slightly different algebraic process in solving, but it's not substantially or substantively different. So it's very similar, and you have a similar certificate, integer certificate, to decide whether something. Once that somebody gives you that certificate, you can verify whether the solution exists or not. So so in general, if you have a graph which has such a recursive decomposition into rigid subgraphs, where each rigid subgraph has itself finitely many solutions, so you can sort of pick out one solution for each from each subgraph, and that it corresponds to an integer certificate telling you which of those solutions to pick at each time. And so essentially, if you have a constant size DR plan, which means that at each node, when you decompose it into its sub-rigid subgraphs, each of which has a constant number of solutions, you have only constantly many subgraphs within each subgraph. So as shown here, there is at most 3 subgraphs within each subgraph here. And if that's the case, then again, you can specify the particular solution you have to pick at every stage, and as a result of which you have an integer witness, or so as a result of which you can, for any constant degree graph, dr plan graph, constant size, constant degree dr plan graph, you should be able to do exactly the same thing and put the problem in NP. So extending this a little bit, you can try to, instead of thinking about the particular solution, so if you think about it here, for each of these subgraphs, you're sort of specifying out of the finitely many solutions, one solution that you're going to pick, and that gives you the certificate. Now you can ask yourself, what are the ways in which you can index that particular solution? You can simply give them numbers, but then you would like to have a geometric meaning for what one particular solution is as opposed to another. And a standard way to try to do that is to sort of use critical points to say, I want to pick the solution between this critical point and that one, or between this critical point and that one, or give orientations, which also corresponds to orientations of solutions. So this, we'll see a little more of this later. So in this example, you have this graph which is not tree decomposable, and in this case, you see the 2 solutions, and you can sort of describe this as critical points. The 2 solutions, as you see that V3, V4 are in opposite positions with respect to V0, V1, but they're also in opposite positions with respect to this other edge, which can be used in the dr plan successively to find the possible lengths of V3, V4, which then will allow us to solve the entire graph. Okay. So you can ignore this. This is just a larger version of the whole thing. So to talk about the dr plan, so now that we have motivated why dr plan is something that helps in 2 different ways. One is to reduce the we motivated in one way, which is to give a certificate for the particular solution that you care about, so that once the certificate is there, you can check whether that solution exists in polynomial time. But there is another much more important reason for talking about dr plans, is that in general, polynomial system solving comes down to using Grosvenor bases or anything else results in a triangularization of the polynomial system. But then it's a sort of a generalization of Gaussian elimination and GCDs, and you eventually end up with a single univariate polynomial in very high degree, and you have to take the possible solutions and then substitute them into the previous and do back substitution and solve it. Now, this is in general not polynomial time verifiable. And as far as deterministic algorithm, it's a double exponential time deterministic algorithm. So I put some references here for people who are interested. You can ask me later. So I've been working in this area of dr plans for a while towards the problem of realization, and several papers have appeared since 2001 in various places. So if you look at the other way of thinking about, I just wanted to, again, for completeness, mention the other way of thinking about solving this system by filling in the distance entries and then potentially using the distances. You can also, instead of the Grosvenor generators of the ideal, you could potentially try to think of the ideal of the Cayley Menger polynomials. Again, you can think of 2 possible ideals. I've been thinking about this for recently quite a bit. So one is the vanishing ideal of the principal minors, which correspond to these determinants that of the simplices. and the other is the vanishing is the ideal of all minors. And Ileana gave a talk in which she was using this and a definition of algebraic matroid that comes from this ideal, which is a prime ideal that gives a definition of a matroid with a unique irreducible polynomial for each circuit. There's another way of this other ideal, which just refers to the principal minors. Both give rigidity matroid. So in terms of just circuits and dependencies, they both serve the same purpose, although the ideals are different and the definition of circuit polynomial is different. So one way to, as Ileana talked about, essentially by using this way of generating circuit polynomials, you can potentially speed up the process of, if you have to use Grotma basis, you can potentially speed it up because there's some term order that kind of falls out of this. So, when we use the DR plans, there are some things that we have to still watch out for, is that we need to use the critical points to isolate the roots, and somehow we need to be able to specify which root corresponds to what certificate. And if you, you may still end up with relatively high degree polynomials and still not have a polynomial time verifiable certificate if the size of the DR plan is very large, is not constant size. So the constant size DR plan, you should realize that, in a way, when somebody gives you the Henneberg 1 construction or the tree-decomposable construction, that's automatic. But the DR plan is itself part of the certificate. So finding the DR plan is itself a hard problem. So, to find the DR plan, which is itself a certificate, you need to be able to do that in polynomial time. Turns out that if the graph is not minimally rigid, we don't know. And in fact, in some cases, we can actually show that it's finding a DR plan that minimizes the maximum fan-in, which is the size, is itself NP hard. So in general, for 2D bar joint system, if you have a dependent graph, so this is kind of counterintuitive because one might think that if you think of it as a completion of the Euclidean distance matrix, the more distances are given, the better. But it turns out that, there is a sweet point. I mean, there are certain sets of distances, if dependent distances, if they are given, it's good, such as D+1 lateration graphs. But otherwise, it may actually complicate matters. So basically, the problem is that you might have for dependent graphs or over-constrained graphs, such as this one in 2D, you can have multiple DR plans and with vastly different sizes. By size, I mean the total number of children of any given node. So as a result of which, finding the optimum one, or the decision problem of is there one DR plan where the number of subgraphs at any given graph is small, constant size, some fixed constant size, whatever size you give, that's an NP hard problem. So, but we were able to show that if the graph is minimally rigid and you have some conditions, so in this particular case, the 2D rigidity matroid is also a sparsity matroid. So some operations can be done quickly, but you can, change this condition to having a rigidity oracle. If you have a rigidity oracle. So in other words, if I gave you a graph to check whether it's rigid or not, and if you had an oracle for that, you would have a similar result in that case. So this is just talking about the decomposition. It's not talking about checking rigidity. So this theorem, so let's for the moment assume it's for 2D, so where we do have a sparsity matroid. So in this case, we have a polynomial time algorithm to get a constant, the optimal size DR plan for minimally rigid graphs. So the general, so once you have that, so you get the recursive decomposition, and then you need to realize the sublinkages corresponding, corresponding to by sublinkages, I mean, for a parent, there are some linkages who are the sublinkages, and then you get their solutions and you combine them depending on what the certificate tells you, which solution to use for each one of them, and then you get the next. You solve the small system, because this is, if it's an optimal DR, if it's a constant size DR plan, great. Then you have a small system here to solve, and then you're done with that. So the definition that we use for DR plan essentially ensures that the subgraphs that we pick are the maximal proper rigid subgraphs of a given graph. Now, and that's how we proceed. So what if there's no constant size DR plan? So we've been thinking both this idea of a certificate, polynomial size certificate, and verification depends on the number of subgraphs that are being joined together at any given stage of the DR plan being a constant size. What if we said that we have a polynomial time algorithm to find an optimal one? Sure, but what if the optimal one is not constant size? And that can happen. And here are some examples of 2D graphs which do not have constant size DR plans. And I'll explain again. It's pretty easy to construct them. There are infinite families of these. Okay, so these are all some examples. And these are all examples you'll see later, even though they look kind of weird. They were inspired by what is called the Berlin graph. This comes from glasses, 2D glasses. And a group in Berlin actually found such structures under the microscope. And then Thorpe and others have found a way to generate these things, just using a program. And so you have these very large planar graphs, which do not, and this doesn't look isostatic, but it has this boundary. You connect all the boundaries together. You have, which I call boundary stiffening. So essentially, so these things, when I say this graph has no non-trivial proper isostatic subgraphs, I mean that nothing bigger than a triangle. So a triangle is the biggest isostatic subgraph it's got. The whole thing is rigid, but it doesn't. So this means that if you try to give a DR plan, as I defined, divide into subgraphs where maximal proper subgraphs that are rigid, it will just basically fall apart into edges and maybe one triangle, right? And so you can create lots of such examples. I mean, there's a way to just create from an arbitrary triangulation. You can create these graphs by just using some flips, etc. Graphs that can look arbitrarily, have very bad DR plans. Okay. So the solution is, the solution that we came up with, which is the work with Mingyu Kang, is to, instead of insisting that the DR plan decompose into rigid subgraphs, allow flexible subgraphs, or not rigid subgraphs. But so in this case, although I'm giving you an example of a non-planar graph, we're going to be using it for planar graphs. So this is K33. So it's just a simple example. It's easy to show. So you would decompose it in this manner. You start out with this four cycle, which has 4 edges, which is flexible. Then you add one more flex. So basically this thing has 2 degrees of freedom. And then you add this edge. Add this edge to get this one more flex. Then you add this edge, remove a flex. Then you add one more these edges to eventually get 2 more edges to get your isostatic graph. So this is what we call a flex DR plan, and it's constant size because the number of graphs that come together at any given stage is in this case no more than 3, and you will no more than 4, and in addition, the maximum, what we call a flex number, which is the maximum number of degrees of freedom any given graph has at any stage, is no more than 2. So now we have one more parameter to worry about, which is this constant flex number, and then we have the size of the DR plan. Okay. So the goal, so we have given up on one thing and we have gained something else potentially. So if we think about this K33 and had to decompose it into rigid proper subgraphs, the only option we would have had is to have all the 9 edges. So you would have the parent, which is the isostatic graph. It would split into all the 9 edges. Because there's no proper subgraph in it. But if you do it this way, then essentially you have, constant size 4 maximum, and you have, on the other hand, you've given up the fact that they are rigid, so you have degrees of freedom. Some people seem to be asking some questions in the chat. Let me quickly have a look. Okay, so just comments. Okay. So the question is, when does a FlexDR plan, by which we're automatically assuming they have constant size and constant constant DOF. By constant, I mean it's independent of the size of the graph. Okay. So there's a theorem that it's not that difficult to show, is that topologically planar isostatic graph with relatively small cycles or degrees of the vertices, then essentially you can get a flex 3 size 4 DR plan, and it can be found quickly. Okay. So so can this be done for all planar isostatic graph? Well, notice that if it's a planar and isostatic graph, it has exactly 1 more vertex than facets. The average vertex degree and facet degree is 4. And we could essentially extend to cycles that are larger. In many of the graphs that I already showed you, you had those 6 cycles and so forth. You can do that. You've got to work a little bit to decide, how to, there's some modification you have to do to the graph without potentially changing too many of the solutions. But that's still in process. So if you do have a good, good planar graph, nice planar graph, I call it, then we can do this. So before we go to the actual method, I just want to describe a particular class of graphs that we're going to use, which are very nice. So we're actually getting a stronger theorem than just getting a flex DR plan. Flex DR plan means some constant size, constant DOF DR plan. So this requires the definition of a particular graph called a type of graph called a 2 tree. What you see here is a 2 tree. It's just a pasting of triangles one on top of the other. This is particularly nice because it happens to be pasting sort of linearly, but not quite. I mean, you have this here. So a 2 tree is obtained by starting with a triangle and pasting another triangle on top of it across an edge, and any other triangle any which way you want. So, and it's clear that this is minimally rigid, and it has some very nice properties. So the existence of a realization of a 2 tree is, of course, much easier because we don't even have to specify which side this, when we add a vertex, we don't even have to specify which side the vertex lies on. For Henneberg 1, you have to do that because depending on which side you put it, further constructions may or may not be possible. In this case, if there's a solution on one side, then there's certainly a solution on the other side as well. So the number of solutions is actually 2 to the n, and it's simple. But you have to actually solve it. Finding one solution just takes linear time. Finding all 2 to the n obviously takes 2 to the n time. So the partial 2 tree is a definition that just is a graph 2 tree with some edges missing, and we're going to be using these. So there's a so remember that we're using planar graphs, and we know that that it doesn't have K33s and K5s because it's a planar graph. But a partial 2 tree is a very specific one, which basically doesn't even have a K4, right? So it's a very small subset of planar graphs. K4 as a minor. No, K33 minors and K5 minors corresponds to planar graphs, and the graphs that we're going to sort of find, locate, or think of this underlying our planar graphs are these ones that don't even have K4s. So there's a theorem that we proved several years ago that essentially says that if you want to parameterize the possible edge lengths or non-edge lengths of a linkage, if you happen to make sure that the edges and the non-edges together form a partial form a two tree. So in other words, if your original graph was a two tree, partial two tree, and you were able, that means you're able to add some edges so that the resulting thing is a two tree, then the realizable lengths of these non-edges actually forms a convex set. So the set of realizable length vectors of the non-edges is a convex set. So we will use this to somehow describe the solutions of a planar linkage using an underlying, so to speak, partial two-tree linkage, right? Or two-tree linkage. And this sort of led to some other results on what we call flattenability, but I won't go into that. So in a way, the way to think about this is just a picture from Wikipedia. There's a formal way of thinking about this. It's called the branched covering map. So essentially what you can think of is that the possible solutions, the Cartesian solutions are the coordinates of the points, are this variety which solves this polynomial system that we had right in the beginning with the coordinates and the distances having been specified. And that's a variety that looks pretty ugly, but we are mapping using the distance map. And in this case, the distance map of the non-edges that I showed, the red dotted ones, these guys, and you get a nice convex set here. So now, and the other thing we know is that given any point in the convex set, you can go back. So that means that you've given these values. And as we said in the previous thing, you can find the solutions to a two tree very quickly. So what we get is a two tree, and now you can sort of find the coordinates of all the points using just the two tree solution. So given a point here, which corresponds to a pair of lengths, you can then find the solutions to the actual thing. So that's given a point here, the inverse map, to get all of these coordinates is a fast process. So this is the distance map. It's a two tree, non-edges of a two tree distance map, and then we can reverse this process very quickly and get the solutions. So so that's the general idea. So here's where we look for the solutions. So I just wanted to give we just got our similar idea for molecular modeling. So here there's a picture. This was in the cover of Journal of Chemical Theory and Computation just in March. And essentially this is our convex configuration space this is the covering map. So this is the covering map. And then this is the upstairs, so to speak, all the pancakes. You can see what a mess it is. And then each of the points here corresponds to a particular realization of these two molecules together, right? And we've used it for several molecular modeling kind of tasks lately, and there's a software available. And here's the Bitbucket for that if you want. So the theorem the stronger theorem that we actually have is not just giving a constant flex dr plan, but actually that for these nice graphs, nice planar graphs, planar isostatic graphs, which, as I pointed out, just don't have very large cycles or large degrees. There is a sequence of graphs, subgraphs that you can find, and corresponding sequence of two trees, such that at each eye, the number of edges that are in the graph and not in the tree versus the number of things that are in the tree but not in the graph, that number is relatively small. And the fact that you can underlie these two trees means that you can solve for these edges that are in the graph but not in the tree using this convexification procedure. So very quickly, so actually this is just the proof of, this should have been a couple of slides earlier, just one of the proofs of 2 or 3 different proofs of how to get that original FlexDR plan using this, FlexDR plan with these 2 trees. But I can show you in sort of a process by which what I mean by this, the difference of TI minus G and G minus TI is less than or equal to 3. So let's say this graph was given to us. So essentially what we would get at the end of this process is this 2 tree. And you can see this 2 tree underlying it is this black part, which is actually a subgraph of this. But it's got some extra green edges, which make it a 2 tree. And the subgraph was actually a partial 2 tree because it's missing these edges. And the original graph, from the original graph, you had to subtract some edges, red edges, to get the black part here, right? So essentially we're subtracting stuff and adding some stuff. So, and the nice thing is that if we can create an ordering such that at any given point in, what we said a moment ago, this ordering, essentially what we get is that as we proceed in this order, as we add, when we come here, for example, we have added 2 of these green edges, and the moment we have added 2 of those green edges, we are able to, in this case, 3 green edges, and we have 1, we are able to realize that 1 edge and then proceed in this fashion. So essentially, if you look at a graph, something like this, you would have added 2 green edges, and that GI will contain the red edge, and the TIs will contain these 2 green edges. So, and then you'll proceed like this. Once you get here, you will be able to, you'll have these 2 guys, but then you have, the old graph is completed. So the new graph will now consist of the 2 new green edges and the 2 red edges and so forth. So, so we can do this for this graph. Again, you start from, you'll add these green edges in between you proceed in this manner, starting from the triangle and then adding a green edge here. And that allows you to, having thrown out this red edge, now it allows you to find the distance of that red edge and so forth. So proceed in this manner. So here's another slightly larger example. These are the given, yeah, okay. So I have until, I have 5 more minutes, right, Tony?
Yeah, you're welcome to 5 more minutes.
Okay. We started at 20, right? 11:20? Yes. Yeah.
Yes.
Okay. And it's a 45-minute talk. So, okay. So, so this allows us, so this sort of shows you the FlexDR plan. Remember, that's how we started out. So we have a FlexDR plan, but something better than just a FlexDR plan, because at each stage, we actually have this branched cover that allows us to solve for these red edges, so to speak, using values of the green edges. So this is just from our software that actually gives us the whole DR plan here, FlexDR plan here. Flex because it's a FlexDR plan. In other words, we have some degrees of freedom in the subgraphs because, if you look here, there are 2 degrees of freedom, 3 degrees of freedom by the time you are able to find the possible values of this edge, right? Okay, so so flex variables. So now I call them flex variables. So in other words, these are the degrees of freedom that are parameterized by the non-edges in that branch covering map. So the map would be to these values of these flex variables, the image of that map. And so these are the non-edge lengths that form a convex Cayley configuration space because they are part of a two tree. And then given these lengths, a realization can be computed efficiently. As I said, for a two tree, the solution always exists. So linear in size and cubic in accuracy, you can find the solution exists if both solutions exist, if one exists. So you don't have that problem of figuring out which direction to go. So essentially, this allows us to quickly find the solutions to this. So, from the polynomial, so just to give a little more, detail on how that algebraic solving process takes place. So we drop some m edges and then we add some m edges. And this is a two tree. What we know is that the dropped edges are the equations that need to be solved, and the added edges are the variables that needs to be solved for. And so in this case, for example, the DR plan C1 and C2 are Cayley parameters that are the dropped edge, red dropped edge, and these are the two Cayley parameters. And then we, of course, use the convexity of the Cayley configuration space of, in other words, in these two parameters, we have a convex space, and then we search. So we fix this, call it C0, actually that's in the next. So you fix, if you have C1 and C2, you fix one of them and find the value of the other one, which satisfies the length of the dropped edge. So this gives us a function of one variable, one of these Cayley parameters as a function of the other Cayley parameter. And then finally, when you have the remaining dropped edge, you would now use a search through all the values of C1 and C2, so to speak, but then now you have C1 as a function of C2. So you're just always solving a univariate system at any given stage. So, so that's just walking bottom up through the flex DR plan now constructs your realization. I have a quick picture here. Let's see, what is it doing? Maybe it went here. Yes, okay, so this is our software that does this. So this is just a simple picture of C1 and C2 and D1 shown here. So for different values, so the depth here is D1, and then you have for different values of C1, you have for each value of C2, what the values of D1 that we care about, and D1 that we care about are around this place. And so this allows you to, because the value of D1 is fixed, allows you to give a function of C1 as a function of C2 or the other way around. So, and then eventually you use this to find the last, the very last dropped edge. So at any given stage, you're always, you fixed one Cayley parameter, you're finding all the other Cayley parameters in terms of it because you have one dropped edge at any given stage. And then, so I hope you're seeing I don't know what people are seeing. Okay, so are you seeing my slides now?
Yes.
Okay, yeah. So now we use critical points to get the combinatorial certificates, and it turns out to be particularly easy because there are not that many different systems that you solve at any given time. There are only a small number of such systems. They look these ways because it's planar graphs, and we have two trees underlying them. So essentially, we are solving red. You drop the red edge, so you're searching for values of given value of a red edge through the different possible values of the green edge. So you have a particular set of small systems that you solve at any given stage, and so you can essentially explicitly classify the critical points, and that tells you which of the different solutions between which two critical points you're looking for at any given stage. So, so basically the main certificate theorem is that for a nice linkage with n vertices, there's a partial two-tree subgraph missing m edges, yielding combinatorial certificates of length n to m. There's a hidden thing here at the very last stage. All of these that I'm talking about are all the intermediate stages, but at the very last stage, you're expressed everything in terms of one Cayley parameter at the end. So now you have to solve for that one Cayley parameter. And that, of course, is not easy. It's not as simple as this. It has all kinds of critical points and can make things very difficult because it's at the end. But nevertheless, we can essentially show that with whatever accuracy you care about in terms of specifying the critical points and solving for the solution, you can do it in reasonable amount of time. So we did this for many examples. So these are the examples that I already showed. A slightly larger example. This is just showing different realizations. As you can see, there's a slight difference between this realization and this realization of a given graph with the same set of edge lengths. Many other slightly larger examples. You see the two different realizations shown in blue and black. Here's another one. Black is the original one, so the blue is different realizations. Whoops, this is the second realization. Some physics, the original Thorpe and Berlin people who had that glass picture, we were able to look at a portion of that graph picture and solve that. So I think I wanted to go somewhere to show you this. Yes, I wanted to show you this. Yes, so these are 4 layers of this Berlin graph. And the system, this is our software, which gives us all the different solutions, as you can see, and tells us, sort of the accuracy of the solution and so forth. And there's another one that we have. Oh, this is the Berlin one. The Berlin one has even larger facets. There's only 2 layers of the Berlin graph. When we use 2 layers, we need to add some extra edges because it's not isostatic when you just take a small piece of it. But we have to add some boundary edges, which we call boundary stiffening. So this Berlin graph is still giving us some trouble, but we are getting there. I mean, trouble in the sense of accuracy. We're trying to get numerical accuracy here. Algorithms wise, essentially the problem is done, but when you actually implement things, take a long time. So that's it. So I think I'm done. Any questions?
Thanks, Meera. That was great. Any questions for Meera?
Lunchtime.
Yeah, so it is the lunch break, but people are welcome to ask questions first. And obviously we've got the long break where the room will stay open so they can have informal discussion if preferred.
Yeah.
Dr. Sitharam, I have a question. So you gave 2 ways of describing a solution for a linkage, right? So one was using the orientation, the other one was using critical points.
Yeah.
So what is a critical point in this scenario? How do you define
yes, that's a good question. Yeah. So so there is no proper definition of orientation when you're solving for this dropped edge, right? Mm-hmm. So let me go to an example, smaller example. Yeah. So so you can talk about when you're solving this system here, when you're solving the 2 tree, it's extremely simple how to say what are the possible positions for 4. That's based on the orientation of this triangle. So if the triangle is on this side or it's on the other side, you get 2 different orientations of the triangle. I can't see my own slide properly here. Okay, of the triangle 7, 4, 8. But when you're solving for the dropped edge, there is no obvious way to describe the roots so you have a particular length for this drop edge and you're searching for that particular length to be attained as a function of these 2 green parameters. And so essentially, if you want that, and even if you fix one of them, let's say for a fixed value of C1, you want the value of C2 that attains a particular length, the different solutions that you get may not have any obvious, it's not quite clear. You could look at all triples of points and try to describe an orientation of this using all the triples, but that doesn't have any clear connection to the process by which you're searching through the roots. What you want is when you're searching through the roots, you know, where's that picture that I had? So if you look through the picture, when you're searching through the roots, you have to sort of say, well, I want this solution and not that one. Okay. And this isn't in any direct correspondence to the orientations of the triangles. So what this is saying is, but on the other hand, I do know that there is a critical point. You know, I can say in general, I can specify any portion of this by just saying, okay, there's a critical point here. I want it on this side or whatever. I can in the end, you know, it's a univariate polynomial, because if you fix, let's go back here. So if you fix one of these, you have, you're trying to find the value of C0 that attains this. So you basically, for each one of these, you have a univariate polynomial whose roots you're finding. So the critical points are clear. So you can then say, I want the one that lies on this side or on that side of the critical point. So it's sort of like if you remember term sequence or other ways of solving high degree polynomial system, high degree univariate polynomials. You sort of isolate the roots between particular critical points, essentially. So you say, well, I want that root, or I want this root. So essentially, that's all this is doing. Since there isn't any obvious, so you want your search for the root to be restricted to the particular solution that you're looking for. And if there's no proper correspondence between orientations and the place, the portion of the space that you're looking for, you can't use the orientations. I don't know. There's a long answer to a short question.